Hello, IB Physics students. We're going to be looking at standing waves today, starting topic C.4. I'll go ahead and give you some illustrations of what a standing wave is, some visuals, and then we'll take the notes and end with some example problems. So if you look on your screen here, standing waves and harmonics, let's consider what a standing wave is. A standing wave is a phenomenon that's created from interference. To get a standing wave, you need two traveling waves, or waves of crest and troughs, or high and low peaks and valleys that are moving towards each other. Say this green one and this blue one that are headed towards each other. As they overlap with each other, they will begin to interfere. So we consider the moment where the crest of one meets the crest of another, we get constructive interference, and we'll get at that place and at that time a much higher peak. And where the two troughs overlap, we'll get a lower valley. But then they'll each shift forward a little bit, and then they'll be out of phase with each other. When they're completely out of phase with each other, crest of the blue will line up with the troughs of the green, and they'll completely cancel out. So as these wave patterns overlap each other, they will momentarily add up and then cancel out with one another. And this can create an appearance where we don't actually see waves moving left or right anymore. In fact, there's no net motion of energy. There's just as much energy going left as is going right. And the pattern is going to look something like this. So in this animation here, we can see two traveling waves traveling in opposite directions at the same time, transverse waves, and then in blue at the bottom is what they add up to. So you notice that as the waves pass each other, we get this fluctuating pattern below, and that pattern is called a standing wave. It seems to stand in place and not move left and right. Of note on the standing wave, you can see there are two dots drawn. There's a place where destructive interference always happens and the medium never moves. And there's a place where there's maximum motion, where it alternates between destructive and constructive interference. At one moment, completely canceling out, and another moment adding up to form a big crest or a big trough. This is called a standing wave, and it always happens when waves are headed towards each other in opposite directions and overlap. These can form a series of patterns depending on how long the waves are, and these patterns are called harmonics. So you can have essentially one lump going up and down, 2, 3, 4, an infinite number of them. Why do we call them harmonics? That sounds like a musical term. Well, let's consider waves in a stringed instrument, like a guitar string. If a guitar string is plucked, and this is very much exaggerated, it's not plucked in the center of the string, but it's plucked off center. And so maybe you pull up or displace the end and you let this thing go. And this particular shape of the string is actually a combination of a number of different waves that all fit in the string. They're considered harmonics of each other. All of these waves, there are 3 of them pictured up here above, they're all pinned down. The strings are fixed at either end. So there's places of no motion at the end. Now, here we've got a big displacement, kind of the 1 lump pattern. The blue is the 2 lump, and then the brown is the 3 lump pattern. You can see in this pattern that if I were to add all of these waves, if they're all present at the same time, you can see how they all have positive amplitudes over here on the left, and they're going to form a big crest like this. Okay. And then over here on the right, there's some positives and some negatives, so there's going to be some canceling. So these 3 patterns form an asymmetric approach like this. So the really fascinating thing, when you pluck a guitar string, your ear is going to hear musical notes. It's going to hear the sounds, and it's going to hear the sound of the red vibration, but it's also going to hear the sounds of the blue and the browns. They're all going to be blended together, which is why we call them harmonics, because generally they sound nice together. This explains some things. For instance, maybe you've wondered about this. You get a musical note. Notes have particular frequencies associated with them. The note E in the musical scale, concert pitch is 320 hertz. So anytime something vibrates at 320 hertz, you hear the note E. But you can tell the difference between an E played on a trumpet, a trombone, or a piano, or a guitar. Why do the instruments have different unique sounds, or it's called the timbre of the instrument? So I collected a little bit of data using a microphone and a sound frequency generator. And you can see right here, I took a tuning fork and I struck the tuning fork. It's supposed to produce the tone E as it vibrates. And you can see what looks like a nice sine wave or cosine wave, which would have the right period and frequency for the note E. But there's kind of some hairiness to it, right? It's this jagged pattern to it. And using a mathematical technique called a fast Fourier transform, I was able to, I didn't do this personally, but the software was able to analyze this wave and pull out all of the different frequencies that are present. And you can see them here. This is a graph. These are the frequencies down here, and then this is the amplitude, or how loud those frequencies are. So there's a big spike. This is right here at 320 hertz for the note E. But you can see there's some other tinier spikes, some higher frequency waves that are blended in, and even a few lower frequency waves that are blended in. And those waves added to it give it this sort of appearance for the tuning fork. That's the tuning fork. When I tried to play the note E through a speaker, I just used the sound generator on my computer and played it through a speaker. Again, I get a big spike here at 320 hertz, but I get some other spikes put in. And even though it's the same note E, it's the same main pitch, these extra harmonics give some color or body to the tone that sounds different than it did with the tuning fork. Interestingly, the most clear or pure tone I got was blowing air through a wooden pipe. This wooden pipe organ, and I blew in it and essentially got just the 320 hertz. And look at how smooth that is. It's more of a pure tone than my computer produced. But there's one right there, a little harmonic thrown in, and that gives a little bit of rippliness to the wave. Most interesting of all of them was the guitar. I took my guitar and plucked the E string. The guitar is well tuned, so it's of course we get in the 320 hertz. But look at these other patterns, and you can see how they're equally spaced with each other. So these harmonics are spaced in equal intervals of frequency, and the guitar wave has a really unique timbre or sound to it, more pleasant sound perhaps than the speaker or the tuning fork, because of these extra harmonics thrown in. So all of these notes are the same note E. They all 320 hertz, but the extra harmonics or frequencies that are also present represent other standing waves that fit in the same string, and that adds to the color of the instrument. Not only stringed instruments, stringed wave is a transverse wave, but air columns can also produce standing waves, where we have sound waves or longitudinal waves traveling through gases. And maybe you've noticed this before, if you've ever noticed how good you sound when you're singing in the shower. So you're singing in the shower and you got these reflective tile or fiberglass walls, and the sound waves are bouncing back and forth, and you find that certain sounds that fit between those two walls of the shower are amplified, they get louder. And so you actually harmonize better with yourself in a reflective body like a shower, because it pulls out the sounds that sound good together and forms standing waves that add up constructively and wash out any sounds that don't sound good together. So you literally do sound better in the shower. And if you think somebody should market that, we do. That's what musical instruments, a lot of musical instruments like a cello or a guitar, these things have hollow air cavities. So you play the strings, then you've got the air cavity on the inside, and the air cavity builds standing sound waves that sound good together. And that also adds to the sound of that particular instrument. It's a little harder to visualize what standing sound waves look like because we can't see the air molecules moving back and forth. So let me see, I got another animation that I could show you that might be helpful for that. Standing longitudinal waves. And in this model here, what we can see with our standing longitudinal waves is air molecules in a pipe. And so you can see the visible molecules moving back and forth. This pipe is opened at both ends. And so the air molecules are free to oscillate back and forth at both ends. Now there's pressure waves traveling. There's one traveling to the right and one traveling to the left. And as they overlap each other, they can form a standing wave pattern. And we can see, just like for the string, we can get a spot in the middle or a place where no motion happens. And we get places where lots of motion happens for our air molecules. And there's quite a pattern of these. So this is one type of standing wave that can exist in this pipe. I could do other higher patterns here. So what you'll notice, and you can see the pattern right here, these things marked in are called the nodes, the place of no motion. So if your ear was in this pipe at a node, you wouldn't actually hear anything. There's no wave or vibration apparent at that location. It's the place in the middle, the antinodes, the A's, where there's lots of air motion molecule for the molecules, and you get the sound. Okay, so that's a higher harmonic, and I could do a bunch of these right here. And essentially what makes these all fit in the pipe is it's the opposite of the string. Instead of being fixed at both ends, it's open at both ends. Now this is a pipe that is open at both ends. I could make it more interesting by fixing one end of the pipe, and this would be more like, say, the body of a guitar. Your acoustic guitar has an opening right by where the strings are, and then the back of the guitar, there's a closed wall. So air molecules can move back and forth a lot at the open end of the guitar, but they're basically pinned against the wall here, which forces a node to exist at that location. I could possibly have both ends closed as well, and then I could have nodes at both ends. And having both ends closed, it starts to look like the same pattern we see for our vibrating string, like the guitar string that's fixed at both ends. So in IB physics, you don't have to memorize the equations for these, but you need to be able to find the pattern and see the pattern based on whether you've got opened or closed ends or a fixed string or a loose string. So we're going to take a look at that. Let's shift to our notes and see if we can summarize some of these things that we're seeing and what looking at a pattern would look like. You want to pull out your notes packet. We will jump in. So we're trying to show what a standing wave is. One really important thing that will probably come up on the IB exam is you should understand that there's no net transfer of energy. When you have standing waves, you have a wave that's going this way, and call this a traveling wave. So a wave that's traveling to the right and carrying energy to the right, and then we have another traveling wave going to the left and carrying energy to the left. But if they're both present at the same time, then there's no net motion of energy. There's just as much energy going both directions as if there's no energy going at all. When these two waves interfere with each other, we'll kind of draw the resulting pattern. Say that they interfere. As they overlap, we'll get places of constructive and destructive interference. And the medium is going to oscillate between different positions. So I'm going to kind of color code this and do something kind of like this. Draw a sine wave that seems to match the ones that are there above. Okay, so we'll use the blue color right there. So at one moment, the medium is going to look something like this as the two waves overlap each other. And then a moment later, it's going to flip. It's going to become basically the opposite. Look something like this. Like so. So we can see that the pattern is flipping between the red and the blue. So there are going to be places where we get constructive and destructive, and the medium's moving up and down like this. And we're going to get places where, as it flips between the red and the blue, no change happens. There's no motion that happens. So we can label these spots. You can see we've got a little key down here, A and N. A stands for antinode. And an antinode is a place that alternates between constructive and destructive. So actually what I've drawn right here is both constructive up and then constructive down. And as it flips between the two, there's a moment where it goes flat, and that's the destructive. So we could label this diagram. All these places in the middle are the antinodes, places where there's all kinds of displacement happening. So there's 6 antinodes in this wave that I've drawn. And then N would represent the nodes. And nodes are places where you always have destructive interference. And those are kind of these dots here in the middle where the medium never moves. The waves always cancel out. So for a string, usually it's both ends, because usually those parts are pinned down. There has to be a node there. Okay, so we got a bunch of nodes. It's like we got 7 nodes to go with my 6 antinodes in this particular arrangement. So standing waves are important because these set themselves up naturally whenever you pluck or strum or draw a bow across a string. So if you look like the violin picture down here below, we need to consider how waves are formed in strings. Now, a useful relationship, now this isn't on the IB equation sheet, so it's not probably one you're going to have to use, but it does show up in the activity. It's kind of something nifty to know. The speed of a wave in a string is described as the square root. I'm not going to derive this. I'll give you the result here of the tension in the string divided by something called the linear mass density. We use the letter mu for that. So Ft is the force of tension. The tighter the string is, that's measured in newtons, and that changes the speed at which the waves travel. So if you've ever played a stringed instrument before, you know that turning the keys and tightening the string, making it tighter, makes the sound a higher pitched sound. Okay. One of the reasons why it makes it a higher pitch sound is the waves are actually traveling faster up and down the string. We'll see how that corresponds to pitch in just a moment. And then we have mu, which is our Greek letter M, which stands for linear mass density, and that's the kilograms per meter of your string. So how much mass do you have for each meter of the string? And so the more massive the string is, so again, think like a guitar, you've got some really thick strings and you've got some thin strings. The really thick strings have a large denominator, and therefore the waves travel slowly. So in the bass strings of a guitar or a piano, the waves travel more slowly. And you can see that that matches with the lower pitch. The thick strings have a lower pitch than the higher pitch sounds of the thin strings. If you flip over to the next page, page 2, we're going to see, and this is basically what IB expects you to be able to do, is come up with the pattern. You should be able to see what the pattern is, thinking about nodes and antinodes and strings, or like a stringed instrument. So we'll see if we can figure out what that pattern is going to be in our stringed instruments of the harmonics that you would hear when that instrument is plucked or strummed. So let's draw some pictures here. A stringed instrument, I can't think of an example where the string isn't fixed at both ends. So there are two places where the string can't move as the waves travel left and right, up and down the string. And so those places have to be nodes, places where there's no oscillation of the medium. And so let's say we have two nodes. So it's basically the length of our string. We'll define that. We'll call the length of the string capital L. The string has the length L. And the simplest possible standing wave pattern that can exist between two nodes is two nodes and an antinode. And nodes and antinodes always alternate with each other. So we have two nodes, there has to be an antinode in between. Essentially what I'm saying is that the string is going to flip back and forth between this red position and this blue position right here. So up and down, up and down, up and down. And really there's waves traveling left and right. They're overlapping to form that pattern. And so we have two nodes with an antinode in between them. Okay. So if you think about this in terms of waves, remember that an entire wave is an entire crest and a trough. So this is the length of a wave, lambda, a crest and a trough, and then after that it's just going to repeat itself again. You'll get another crest and a trough for the second wavelength. If you look at this pattern, how much of a wave are we looking at for the length of this string? So it's either, remember, it's either the crest or the trough. So if it's just the crest, for instance, we're looking at this much of the wave, okay? And if it's just the trough, we're looking at this much of a wave right here. So either way you look at it, if it's just a crest or a trough, that's exactly half of a wave. So we can say the pattern here for the first pattern is that the length of the string is half of a wavelength. Let's think about what other standing waves could exist in this same string. There has to be nodes at either end. So the next one in the pattern would be an extra node in the middle. Okay, so basically we just add a node each time we want to go up one in the pattern. So if we add a node in place of no motion, that means basically this pattern could also exist as a standing wave in this string, where for one moment it looks like this, and then a moment later it flips to that. Okay, so we have two antinodes. And you can see, like, if you look at just the red pattern right here, we're looking at a crest and a trough, or the blue pattern is a trough and a crest. So a crest and a trough, that's an entire wave. So here we see that the length of the string is not half a wave, but a whole wave. And if you like, you could write that as 2 lambda over 2, which is just the same as a wavelength, lambda. You'll see why I'm writing as 2 lambda over 2 in a moment. I think when I draw the next one, we'll have the pattern down. Okay. So again, we have to have nodes at either end. And so in musical parlance, this is called the fundamental frequency. And then we have harmonics, these other higher harmonics that jump in. You don't need to know those terms for IB though. So I have one node in the second one in the pattern. The third one is going to have, and throw another node in there, 2 nodes in between. Something like this. Okay, so then I need to know what this is going to look like. Crest, trough, crest. Okay, so for one moment it will look something like that. And then it's going to flip around, be trough, crest, trough, this. We'll have 3 nodes in between. And in this particular pattern, we can see we've got a crest and a trough, which is a whole wave, and then another half of a wave. So the length of the string, it's all the same length in all of these pictures. And usually, you don't change the length of the string as you're playing it. If you play it open, that is. If you play a stringed instrument like a guitar, you can put your finger on the fret and make it longer or shorter. This one is 3/2 of a wave, 3 lambda over 2. So you can see what this pattern is. We're basically going up, and for our harmonics that can exist in this string, we're basically seeing the pattern as L equals n lambda over 2. And that n is my integers, 1, 2, 3, 4, etc. For as many as I have, I can get higher and higher pitch sounds, because as the wavelengths get shorter, it corresponds to higher frequency or higher pitch sounds that can exist. So just so you know, with the musical instrument, when you pluck or strum a string, the main note you hear is the fundamental. You hear this main one lump going up and down, but these extra higher harmonics and the ratios that they throw in give me the unique sound of that particular instrument. So that's my pattern, and there's an infinite number of these. So the 117th harmonic, I'd just put 117 in for n, and I get a very, very short wave in that case. So in summary, we can say that we know that the way waves behave, the speed of a wave is frequency times wavelength. And it's the same string in all of these cases. The speed of the wave depends on tension and the density of the string, so that's not going to change. So we got fixed speed. So that means as these waves get shorter and shorter, the frequencies have to get higher and higher. We get higher pitch sounds. The shorter waves of the higher harmonics have higher frequencies that sound, we could say, sound good together. There's a mathematical pattern to these, and you can even see that if you're curious. We don't get too much into music theory here, but here is, we're looking at the C scale harmonics of C. So if we play this is a very low note indeed as the fundamental, then the harmonics, and you'll notice that they actually get closer and closer together as you move up the scale. So actually going from a whole wavelength to a half wavelength, or half to a whole, I should say, it jumps by a whole octave. So the first harmonic you hear the C sound, but then you hear the higher C thrown in, okay? And then you get a fifth, and then a third. So you get basically your major scale, and you get, I think I'm doing that right. Well, if you're a music expert, you can weigh in that. It's been a little while since I've done music theory, but at least in the way that humans think music sounds good, matches with the mathematical pattern of these harmonics. So that's the pattern in the string. If you flip over to the next page, another thing that IB would expect you to be able to do is figure out what the standing wave patterns look like in columns of air, and for those patterns. So you should be able to do this for pipes in different arrangements, pipes that are open, pipes that are closed. Different musical instruments will behave this way. I think I mentioned the body of a guitar is like a pipe that's open at one end and closed at the other. Other instruments like the flute are open at both ends. You blow into one end and the other end is open. Or like the trumpet would be an open pipe as well. And you can get standing waves in these, and standing waves happen whenever waves overlap each other. So let's say you blow some sound, you get a wave of pressure. We can draw a bunch of air molecules clumped together. You remember the term for that is a condensation. The air is condensed together, and you blow that in, and it comes flying in at the speed of sound. You get the motion of our wave headed this way, and it's going to hit the back end of the pipe, of course. And as it hits the back end of the pipe, it's just going to bounce off and come back over itself. So if you continue to blow into this pipe or send vibrating air into this pipe, maybe there's a guitar string over here at the left side, we're sending sound in and sound is bouncing back. And as these patterns overlap each other, they can form a standing wave pattern. The important takeaway is that air molecules at an open end are free to move. So the standing wave is going to set itself up. There will always be an antinode at the open end of a pipe. And at the closed end of a pipe, where air molecules are not free to vibrate back and forth, you will have a node. We'll have the antinode-node pattern. So that's air in the body of a guitar. What about in a trumpet? So you blow into the trumpet, and you send that wave of pressure in. You send it flying down this way, and that there needs to be an antinode at this end. where the air molecules are free to move left and right. What happens when that wave of pressure hits the end? Well, you might think, why would it bounce off? There's nothing for it to bounce off of. It's just going to head out. And you'd be right about that, right? That wave of pressure is going to head right out the end. But there is going to be a reflection nonetheless. The reflection happens at this boundary. It's a reflection of the opposite type of wave, okay? Because it's a different medium. It's constrained air to bulk air. And so what ends up bouncing back is not a region of high pressure, but a region of low pressure. Bounces back in the opposite direction. And so we get, if you recall this funny term, we get our rarefaction, a region of low pressure bouncing back in the opposite direction. And we still get waves crisscrossing each other and forming the standing pattern of waves. So in this case, we'll have an antinode at both ends. It's basically the opposite of my string, which is nodes are fixed at both ends. They're antinodes at both ends of an open pipe. There are some instruments that have both of these happening at the same time. A pipe organ is a good example. Half of the pipes in a pipe organ are closed and half are open at both ends, and you can get different sounds, different standing wave patterns existing in these different pipes. So what are the patterns? How would you come up with them if it shows up on the IB exam? Let's see if we can do the same thing we did with strings. You should see a similarity. So in the case of the open pipe, let's use the same sort of terminology. We'll call L the length of the pipe, just like L was the length of the string. And the difference is instead of nodes, we have to have antinodes at the ends of the open pipes. Okay. So what do I have? What's the simplest possible pattern that can have an antinode at either end? Since nodes and antinodes alternate, there has to be a node in between. And I know these things are vibrating left and right, but we're going to draw them the same as we draw transverse waves in a string, just to show that the fluctuations have maximums in certain places and no place of fluctuation in others. So I can do something like this, going from node to antinode. And it's fluctuating back and forth. And what this represents is that it's moving back and forth a lot at this end where there's lots of displacement happening. This is a place where no displacement happens. Or if you had your ear, you would hear nothing. You get destructive interference. So again, well, the important thing is recognizing how much of a wave this is. So if we look at, for instance, at this red part of this pattern here, where it goes from crest to trough, from crest to trough is from here to there. Okay, that's the fraction of the wave we're looking at. So that represents half of the wave from crest to trough. So it's actually very much like the string. The simplest pattern is half of a wave. It's lambda over 2. L equals lambda over 2. The next one in the pattern, again, we got antinodes at both ends. We put one node in between for the first one. So now let's put 2 nodes in between for the next one, which means we need another antinode in there too. And draw this pattern. We look something kind of like this. And by golly, we're going to get the same pattern that we did for the string because there's the same thing happening at both ends. Okay, so we go look at the red one here from crest to crest. That's an entire wave. So the length of the pipe is 1 wave or 2 lambda over 2. So I'm expecting, we'll see that same kind of mathematical pattern. I'm expecting 3 lambda over 2 for this one, a wave and a half. See if it comes out that way. We have antinodes. And then instead of 2, we'll put 3 in there, 3 nodes. I'm going to stop putting A's on there because my drawing is getting a little cluttered. Drawing these dots is going to help me then to form the pattern. Look something like this. Like this. So sure enough, we look at the red, I go from crest to crest, that's a whole wave, and then another half of a wave there. So we have a wave and a half. Okay, so that's the pattern of lengths and the not the frequencies, but the wavelengths they produce. If you like, we could write this in terms of frequency, and that's something you should be able to do or come up with. It's going to be the same exact thing for the strings as this, so I don't need to go back and do that there. But if we look at this one, what I could do is I could rearrange this and say, okay, the wavelength that I'm hearing, if I solve for that, is equal to 2L, twice the length of the pipe. Okay, this wavelength is just equal to the length of the pipe. And this wavelength is equal to 2/3 of the length of the pipe. if I solve that for lambda of the sound that I'm hearing. And then if I want to know, usually it's the frequency we want to know because that corresponds to the musical note. The frequency of a wave is equal to the speed of the wave divided by the wavelength. Frequency is equal to V over lambda. So since lambda is 2L, I could say the frequency of the wave is the speed of the wave over 2L. So when you blow air into a pipe, what's the main sound that you're going to hear from that pipe? Depends on the speed of sound divided by twice the length of the pipe. So the longer your pipe gets, the bigger your denominator becomes, and the smaller the frequency becomes. We get the lower pitch sounds for the long pipes with the low frequencies. So this is the first one in the pattern. If we do that for this one here, the frequency is the speed over lambda. We get V over L, okay, instead of V over 2L. And then if we do it for this one, we'll get, say, 3 V over 3/2 L. So I want to write that, not like that. It's the inverse, so it's instead of 2/3, it's 3/2. So we'll say 3V over 2L. So if you want to write the pattern, you can see there's a mathematical pattern here that the first frequency you hear, okay, corresponds to 1V over 2L. The second frequency you hear corresponds to 2V over 2L, and the third frequency corresponds to 3V over 2L. So we've come up with a basic pattern here where we could say the frequency of the nth harmonic is equal to NV over 2L. So I want to know what the sound of the 200th harmonic is. I could put 200 in for N, and that's going to be a really high-pitched sound. So we get all of these harmonics, and the basic harmonic was equal to V over 2L. So they're all multiples of each other. We could also say in general, the frequency of the nth harmonic is just equal to N times the first one. So if you know what your basic note is, you know, the 20th harmonic is going to be 20 times higher than that. Okay, so it's exactly the same pattern for the string fixed at both ends. So if we flip over to the last part here, let's just look at one that is a little bit different. A pipe that we have some asymmetry here. Again, like maybe the body of a guitar, open end, closed end, and see if we can come up with a pattern for this case. So again, we have the length of our pipe. I'm going to blow some air into this. The difference is the closed end has to have a node. The open end has an antinode. So I'll get a string here. The most simple pattern, antinode, node, I don't have to put anything in between. They alternate with each other. We can have the antinode to the node, something like this, crest to midpoint. There's my simplest pattern. And again, if you think about what does a whole wave look like, I'm going from here to there. It's this fraction of a wave. So instead of being a half a wave, now we're talking about a quarter of a wave. So for the first one in the pattern, we can say L is equal to 1 lambda over 4, lambda over 4 for the first one in the pattern. Let's see if we can figure the rest of the pattern out. So we got node, antinode. Just plop another node in there. So all you do to go up a harmonic is throw another node in. We go through this node and then to this one. And like so. Here's the next one in the pattern. So how much of a wave are we looking at there? This is a little bit tricky here. So we're going from crest to trough and then back to equilibrium again. So we're starting here and we're kind of going to here. We're going like kind of this span right here. So it's not quite a whole wave. It's actually 3/4 of a wave. So L equals 3. And my pen's dying here. Let me find a pen that works. 3 lambda over 4. L equals 3 lambda over 4 for the next one in the pattern. Think you know what the next one after that is? Let's see, node, antinode. We had one node, let's pop 2 nodes in between. Node, node. We're going to look something like this. Next standing wave that fits in there, a higher frequency. How much of a wave are we looking at here? Well, we go from crest back to crest again. That's a whole wave, and then another quarter of a wave thrown in, so a whole wave and a quarter. So here we see L is equal to 5 lambda over 4. So what's interesting about the pipe that's fixed at both ends is rather than having all of the harmonics, we have what's called odd harmonics. You see the pattern goes up 1, 3, 5, 7, 9, 11. Okay, so I keep going up by odd numbers. So for a pipe that's closed and opened at one end, there's no such thing as the 20th harmonic. There's a 19th harmonic and there's a 21st harmonic, okay, but it's going to go up just by the odds of the pattern. And so we get something very similar if you do the wavelength to the frequencies of the sounds that show up in this pipe. The first one is V over 4L, and then we get the next one is 3V over 4L, and the next one is 5V over 4L. So we're going up by odd numbers. So the frequency of the nth harmonic is equal to NV over 4L. And again, V over 4L is the fundamental, the main note, for the frequency of the nth harmonic, just like for the other string, is equal to, they're all multiples of the first one. The difference is n isn't all of my integers. Now n is only the odd numbers, 1, 3, 5, 7, 9. Okay. Now, these equations, you're not going to have to memorize these, but you might have to come up with them. You might have to drive or put them together as you solve problems. So that ends the lecture. We'll look at some example problems in the next video. I hope this is making sense. We'll find out.